So our next speaker is Abhishan Ravikumar, who's at Oxford Brookes University, where he's a PhD research student, but he's also doing some work for Infineon Technologies based in Bristol. The title of his talk is an AI-assisted connection weight prediction for regression testing of integrated circuits. He specializes in IC verification, working on optimizing test selection methodologies to enhance verification efficiency, leveraging machine learning and graph-based techniques. Collaborating with Infineon Technologies, they aim to develop novel approaches to circuit validation that ensure robust, high-coverage testing strategies. He has a background in software engineering and quality engineering, has published research papers on AI-driven verification techniques, and continues to explore the intersection of AI and IC verification. This work contributes to advancing automated verification methods and reducing time to market for complex IC designs. He's located in the UK, as I say, Oxford Brookes University. Okay.
All right. Thank you for the introduction. Good evening, everyone. My name is Abhishan Ravikumar, and I'm a PhD student from Oxford Brookes University in the Advanced Reliable Computer Systems group. So my supervisors are Dr. Alexander Rust and Dr. Busale Jabir. So this research is a collaboration between Oxford Brookes University and Infineon Technologies, where we will be focusing on optimizing the IC design verification process assisted with AI. So in this presentation, we'll be going through the motivation of this research and some related work around IC design verification, then a brief introduction for a particular test scenario, and connection weights and why it is important in this particular research work. And towards the end, we'll be also going through the research approach and implementations, and also some results we got from this particular approach. Right, so integrated circuits are combinations of electronic components, and that basically performs a specific function. And IC verification is a process of ensuring the design is correct. However, verifying that an IC design is correct can be very resource intensive. So when the design becomes more complex, the cost of testing is also going to rise, and it becomes nearly impossible or impractical to test the entire design every single time you make a minor change in the design. So this is where we need regression testing. So regression testing basically focuses on checking the changes made to a particular part of the IC design, and the check is basically on to check if the change you introduced have not impacted any existing functionalities or the blocks in a particular IC. So this approach basically ensures the IC design remains robust and reliable, while also saving both time and the resources. So therefore, optimizing the IC verification process is important to keep pace with the rapid technology development, and also to deliver high quality products in the market. Right, and like a perfect example for this would be the Intel FPU bug, which happened in 1994. Intel faced a bug with their FPU algorithm, which created incorrect results for particular scenarios, per se, for experiments. So in which they had to spend up to $435 million US for chip replacements and reimbursements. Another example would be the Apple A11 Bionic chip that had a defect with the touchscreens, and that is also due to an IC fault. So there are many examples like this in this industry. So these aspects basically highlights the importance of detecting bugs early in a complex IC design, and detecting bug early would give us the functional correctness. It makes the IC design more reliable, and the overall quality will be good. So there are certain factors that makes an IC complex. So factors like the transistor counts, functionality, how well they're connected with the blocks, and the strengths and the connections between blocks within an IC. Right. So in this research, we will be working on a circuit with the tri-core architecture. So this is from Infineon Technologies. So these types of circuits are mostly used in both automotive and the aerospace industry. Right. So the challenge here is that verifying an IC design requires millions of test executions depending on the complexity. So the main challenge here is to select one small portion of the test from this large pool to efficiently and quickly target a specific change you made in the design. And the related work around this area would be the simulation-based verification that basically offers a framework to test designs across multiple scenarios in a particular IC. Meanwhile, regression testing also focuses on specific sections of the circuit that have been modified and making it more efficient to verify the change you made without retesting the entire circuit every single time you need to do a test. Right. So SMART Regression testing is a proprietary product from Infineon Technologies, which uses basically the nearest neighbor algorithm to select test based on the geographical closeness of a design block. So as you can see here, the SR contains three phases. So one is to define the design and their properties, and also it also involves grading test based on the properties. And phase two is to create a test distribution that is creating a scenario for a particular test design. And finally, we'll be using the nearest neighbor algorithm to qualify the test for that particular regression run. So in this aspect, the key to this method is accurately measuring the connection strength between interconnected blocks, known as the connection weights. So this is the key part of the SMART regression. So to improve this process, we proposed an AI-assisted method for predicting connection weights between design blocks, which basically enhances the efficiency and the test accuracy, basically the test coverage when you run a particular regression. Right. So in this regression test scenario, it is important to distribute the test across all the connected blocks. The distribution of these tests are influenced by the connection weight, which I mentioned in the previous slide, which basically represents the strength of a connection between two blocks. For example, like a connection weight ranges from 0 to 1, with higher values indicating stronger connections between the blocks, and lower values indicates a weaker connection. That means connection strengths with high value will need less number of tests, whereas connections with lower value will need more number of tests, because the chances of covering both the blocks together will be less when the connection strengths are low. So this distribution is very important in this case. So this ensures the testing is focused in areas where the changes are likely to impact the design. So this is where we use graph neural networks that operates on a graphical data structure, making them more ideal for these types of regression testing. So the approach here is to replace the manual method of generating the knowledge base for testing. For example, the connection weights previously have been done manually with the expert knowledge of a design engineer. So we will be replacing this method so that it can be consistent throughout the testing phase. So by using this approach basically uses message passing neural network layer, where graph neural network collects information about the closest or the connected blocks to improve the representation of a particular block, or in terms of graph neural network, it can be called nodes within a graph, and leading it to giving more precise information about a particular blocks and its connections along with its properties. So this is the overall approach. So we convert the circuit into a graph where where the nodes represent a component and the edges capture the connections between them. So graph neural network uses message passing layer to exchange information among these nodes over a multiple layers. So in this case, we'll be using 4 layers, which so each node will be represented as a refined property, and those informations are gathered by the connections they have in a particular circuit, and that gives us a detailed view of the entire circuit in a graphical form. So we'll be using this data for our model. So with data analysis part, so we started by gathering data from custom designs, which includes both design specification and connection details between various blocks. So from there, we refine and organize the information we got, and we put it to a feature table with each block represented as a node in the graph neural network. The next step, we correlated the overall IC design to create a fundamental connection table, meaning a basic knowledge base for our model. And finally, we reconstructed the table, which contains every possible connections and ensuring all the blocks are connected to each other in multiple levels. Again, giving us a comprehensive mapping of the design's interconnectivity. So even if two models are not connected, it will still show some connections where we will be using it for our prediction. Right. So this model basically uses the encoder-decoder approach. So the encoder contains 2 graph stage convolution layers to accurately represent each node, as I mentioned before. And basically, they function as the message passing neural network layer, which passes information from the neighboring nodes to improve node representation. So the layer is organized in a way that the first stage layer feeds into the second one, capturing high level of representation of a particular node and their dependencies in their graph. And to introduce non-linearity, ReLU activation function is used. So that basically is followed after each stage convolution layer that allows the model to kind of learn the patterns within the connections. And finally, the decoder layers basically takes the encoder's output and processes it through 2 linear layers with, again, the same optimization activation, predicting connection weights between 2 blocks. And finally, we have an optimizer as well. So for that, optimizer is basically used to optimize the predictions, the results we get, and continuously update the database we have, and then use that as the knowledge base for the next training phase. So this is how the structure is arranged. And this is how the data is prepared. So in order to come up with these weights, we had to use some of the attributes. So to predict connection weights, we considered the number of incoming connections and outgoing connections, which again will be detailed in the design. The number of car points each, a car point basically represents the point in a design that needs to be tested. And we'll be listing that as well. And finally, a binary value of whether a particular block is self-connected or not, which means basically a particular block has a connection to itself. So basically using its output as the input for the next cycle. And the block instinct weight indicates the priority related to the other connected blocks. So these attributes help us accurately kind of predict the connection weights, leading to more efficient test results or test selection phases. Right, and so we assign the priority for each of the attributes, and obviously we can change it, but according to this particular design, we stick with this priority levels. And based on these priority levels, we calculate the priority score of each block. And with the use of these block priority scores, we'll be deriving the connection weights at each level. So in this case, we've considered up to 3 levels. Right, so the model evaluation. So for training the model, I split the data set to 80% and for training and 10% for testing and 10% for validation. So we tested our model with a 535K micrometer square design using a 28 nanometer technology. The design includes various components such as FPU, decoder, load unit, ALU, etc. So there were about 13 blocks altogether in this particular circuit we tested. So in total, we have around 33,000 test cases where we consider both covering good and bad results. So good results meaning they have a high coverage for most of the blocks. So this comprehensive test set allows us to evaluate the effectiveness of our model. So based on the training, we predict the connection weights and selecting the appropriate test for a particular scenario. So the graph you see here are the training losses for both the training data set and the validation sets. As you can see, the error from the predictions are lower towards the end of the repetitions, so which is at 300 epoch. Right, so here are some results. So to check prediction accuracies, we compared the predicted and the actual connection weights, averaging at around 80% accuracy. And using the block interface unit block, that's one of the blocks from the circuit we tested. So we tested our approach against full regression, random test selection, and the proposed method. So the proposed approach gave us the highest coverage comparatively to the other methods. So we used expression coverage and the total coverage in order to compare these results. And additionally, we also compared our results with a random test constraint approach that uses machine learning for test selection. Although it produces, as you can see, it produces high coverage, but the number of cycles and the test was not ideal for the regression testing. So in this case, it's using 15,400 K cycles. So that multiplied by each time a test takes to run. So that's not ideal for a regression, which would take nearly a few days for that execution. So since we are focusing on regression, we are doing good results. So overall, we are doing 91% coverage with 100 tests for execution time for 50 minutes and another 20 minutes for the report generation. Right, so this research is a published work which was presented in the 37th DFTS conference. So please feel free to go through the work, and if there's any discussion, we can discuss it. So in conclusion, our AI-assisted weight prediction method for the regression shows us promising results, and we are continuing to build to automate other stages of the regression part using AI. And also for future work, this research is directed towards automating and being able to select tests for, basically select tests without being test or circuit dependent. So in this approach, we totally use data from the circuit, and then the results we get are compatible only with this particular circuit. So we are focused on improving that, and we also have some other future results as well. So hopefully it should be out soon as well. So yeah, that's it. Thank you. Any questions?
So just check online for questions. You sure there are any questions, please?
Yes, one question.
Can you type it for me?
Yeah.
Yes. Can you offer more details about how the connection data is obtained? So connection data. So I believe you're asking how the connections are obtained. So basically, each circuit comes with a description, and we also know the cover points of all the blocks, and also we know details about each of the blocks. So from that, we'll be obtaining the connection weights from that. So basically, what our model does is predict the connection weights. But initially, it was manually presented to the nearest neighbor algorithm in this smart regression testing, which is used in Infineon. So yeah, so we'll be using this test knowledge base, and then we'll also be using the test gradings to come up with connection weights. I hope that answered your question. That's you.
Okay, there's one more.
Yeah.
Is
so
this
this is mainly
for SOC verification, or do you use it for IP too?
I'm sorry. Can you repeat the question, please?
Is this mainly used at SOC or subsystem verification, where you got multiple blocks, or can you use it IP level too?
I think right now it's mostly on ICs. So I believe you can do it on both, but then this research currently focuses on the design aspects currently. So basically, we rely on simulation data.
There's 3 questions in the audience now. Do you want to go?
So does your example use select or highly randomized tests?
Did you hear the question?
Yes. Is it the question from the meeting?
No, it's how do you. So when you exclude tests, how do you make sure that the features that they were verifying are still being verified?
Well, yeah. So once we select the number of the connection weights, we use the smart regression to give us qualified tests for a particular scenarios. And based on the selected test, we pass it to a simulation from Infineon Technologies. And that basically gives us a report and the coverage that particular test suite has covered. So based on that, we ensure that if a particular block is covered or not.
So you make sure you still got the same level of coverage. Yeah. There's one more question. Is it on?
Yeah.
Comparison with the code coverage of the SAP. He was talking about full regression a randomly generated test selected. Have you tried with the normal ranking for the come for free?
Yeah. Did you hear that question? I thought it was a bit of an
No,
echo.
not really. It was not clear.
So I'll tell you what the question was. Normally within the EDA tools, you can rank tests based on effectiveness. So and you can do that without AI and maybe just select the top ones. Does your method give any advantage over that? Just that ranking method?
Well, this model basically does it for particular test scenarios rather than testing the entire circuit at the time. So for example, for one particular scenario, let's say we are testing maybe the first 10 blocks, and we make sure that model gets that feed as an input. And based on these results and the connection weights we predicted, it'll make predictions according to the selected test rather than the entire circuit.
So you're basing it on a reduced scenario rather than the full suite of tests, I think.
Yeah. We use the entire test pool for selection purposes, but then when we select it, we only send a portion of it, maybe around 100 or 200 tests for a simulation.
Okay, thank you. One more question from Bristol, and then we're...
Exceed achieved by full regression and...
Sorry, can you speak up, Gav?
Yeah, so the question was, using a method, did you manage to...
Hang on. Yeah, sorry. It's speaking to me. Sorry. Yeah, go ahead. Yeah, go ahead, Gareth again. So we're going to get the question first, and then you can give the answer, please. Yeah.
Yeah. So using a method, did you manage to get or exceed the 94%?
Yeah, hang on. Yeah, can you?
cover?
Please listen to the question first. Yeah, go ahead.
Okay.
Gareth.
In a comparison, 100 tests.
Abhishan, there is a question from
Much lower
at the
than
venue,
coverage.
from the
Okay.
venue.
Yeah.
Sorry. Yeah.
What are the implications of making that the same or close to the same? Because obviously there's a I don't know 4 or 5% difference in coverage.
Yeah.
Why not have similar level of coverage in the automated test? Not 100 tests or 150 tests or 200 tests or however many tests it is.
So-
Makes sense.
No, sorry. You're going to have to repeat the question again.
In the comparison
Yeah,
of 7,000 tests versus 100 tests,
yeah,
coverage was 5% lower.
yes.
Can you make it higher, basically, so it's more of a valid comparison with a similar coverage percentage?
All right. So you want to? So the question is, can you get to the same level of coverage with fewer tests, or much closer? Yeah. So your drop was about you reduced from 27,000 to 100 with a 5%. Maybe if you dropped from 27,000 to 1,000, you would have got 2% difference. Did you look at that? And so you could trade off coverage loss versus regression speed. Did you do that trade off?
So let me clarify the question. So the question was, if you reduce the number of tests in the test pool and then do this connection weight prediction, is it giving any better results? Is that the question?
I guess the question is, so you've gone for 27,000 down to 100 with a 5% loss.
Yeah.
Okay. But that's on the sort of sliding scale. If you'd done 1,000 tests rather than 100, you may have got only a 3% drop. And the customer may say, well, that's better actually. So did you trade off the loss in coverage versus the drop in performance?
Well, yeah. So the point of a regression is to quickly test a particular change you make. So in this, since we are using 100 tests, so it's almost an hour of testing time. But in that case, if you use 1,000 tests, it's going to take longer. So I would assume it's more than 10 to 15 hours in that case. So I think that trade-off is not ideal, because even if you do 1,000, as you can see, the results are almost closing to like only a 3% different, right? So even if you do 1,000, I don't think there's going to be a lot of changes, and the trade-off is not worth it in that case. So the main target here is to reduce the time taken to execute.
Okay. Okay, thank you. Yeah. Okay. Last question in the audience from Bristol. Yeah, go ahead. But I think that was the question here, and it's because normally the ranking tools do the whole SOC rather than target the particular change that you've made. So they target the particular change that you've made. Yeah. So if you say I've changed this block, tell me all the main blocks that are connected to it, then you can have higher confidence with much reduced performance. I think. Yeah. Yes. Yeah, it's for the specific thing rather than the whole coverage. So I don't think they've done that. Okay, thank you very much.